Thank you all for coming out and not taking a nap after lunch. You know, as I've been mentioned, I've been doing various things over the course of the last couple of decades to try and improve password usage. I started off with I actually posted something to sci.crypt asking people to send me their PGP passwords on a postcard on the theory that, you know, don't put any identifying information on the postcard, and quite a few people did, and I put out a little survey, and sure enough, most people were making really weak passwords. Diceware hex is I think one of the earliest, probably the earliest memory-intensive hash, and Diceware is doing very well. People have, on their own, translated it into a number of languages, the instructions, and there are currently Diceware word lists in 17 different languages. How many people here are familiar with Diceware, have seen it, or how many use it? Right, that's par for the course. Okay. Another little thing I did was, this is a Diceware, we're taking a random set of 10 letters and producing a sentence. There's a lot of password advice to take a sentence and use the initial letters as the password. Problem is people are not very good at coming up with random sentences, and the distribution of letters at the beginning of words is not that random. This guarantees it's all uniformly distributed, and any 10 characters you want, you can get a sentence out of it to help you remember the password. It's not my day job. I've done many other different things. I've also, among which is I've written the security chapters of a number of different dummies books, including Email for Dummies. It turns out when Hillary had her 50th birthday, she got a copy of Email for Dummies from her staff. I'm not making this up. It was reported at the time in Newsweek, so that she could send email to her daughter who was going off to college. And so anyway, it's all my fault. Okay, so today's problem, I keep looking. I have this thing right in front of me. I don't have to keep looking at the screen. Today's problem is protecting passwords in the enterprise. What I'm talking about today, Roxol, is intended to target enterprise scale systems. Big systems, many users, server farms, e-commerce, you know, serious value at stake. There's a whole other class of passwords that are used to generate more or less directly cryptographic keys. The PGP and GPG use it. Disk encryption systems use it, Wi-Fi, and password managers and Bitcoin wallets. In those cases, you know, I still say, you know, pick systems that use good key stretching, use Diceware, and contrary to a lot of advice, write your password down, because that way you'll pick a password strong enough to remember it, and no, don't put it on a post-it note next to your screen. Okay, so back to the enterprises, which is the topic here. Enterprises have a problem. They have to store for every one of their users some information that can be used to validate a password when it's entered into the computer. And although many people keep talking about the death of passwords, they're not going away anytime soon. The enterprise can do things like throttling how many online login attempts happen per unit time, but there's this whole problem of offline attacks. The difficulty is that databases that are in use are very hard to protect. The databases are frequently stolen, and just encrypting, people will say, well, just encrypt the passwords. I think, as most of you know, it's not that simple. There have been many database breaches. Here's a few there's a list of them on Wikipedia. You know, companies that should know better, including RSA, have been hacked. It's very hard for middle-sized companies or any kind of enterprise that doesn't specialize in the topic to do an adequate job. I went to my local business school had a conference on computer security, and this is one of the slides that was up there, a couple of quotes. The favorite being, there are only two types of companies left in the United States, those that have been hacked and those that don't know they've been hacked. The other line at the bottom there, the best way to protect data is to get rid of all humans. Plan B is to train them. Plan B isn't working either. And I think we need to go to Plan C, and Plan C is, can we find a better way to protect passwords that are being stored? Okay, the existing methods are inadequate. Obviously, the worst case is just to store the raw password. There are still some people doing that, unfortunately, we find out. Simple hashing, there are problems with that because you can build rainbow tables and whatnot. Salted hashing, computational intensive hashing, all these things are increasingly vulnerable because, as you'll see in the next slide, the computing power available to the attackers is just getting larger and larger. So people have come up with the idea of memory intensive hashes that pushes the threshold a little higher for the attackers, but it's still expensive for large users of multi-user systems. They can't tie up a server for several seconds for every person who's trying to log in, or at least they could, but it's expensive. And we still have the problem that the weakest password can compromise the system, so that if you're once you're in, then you have the whole panoply of escalation attacks available to you. So and all these things, they help, but they don't really solve the problem. Keyed hashes was mentioned earlier today in the NIST presentation. It's a good solution, and in some sense you'll see rock salt has a lot in common with that, but it's still a single point of failure. We don't know how exactly we store these. The key for the hash, it's a very small value. We don't even know if it's stolen or not stolen. Okay. So there's an arms race going on here between the protectors of password validation data and the crackers are winning. And there are a bunch of reasons for that, one of which, of course, is our favorite Moore's Law. That's another thing. I guess Moore's Law and passwords have a lot in common. Their death is always being predicted. But they never seem to quite die. But another big driver of that is gaming. Computer gaming is a major driver of the industry and has focused a lot of development work on building very high performance graphics processors. And modern graphics processors, it turns out, are just more than adequate for calculating the standard hash functions, which means that they are very good at attacking large numbers of, doing large numbers of password guesses at the same time. So even though the hash is salted, the GPUs can handle that. Memory intensive hashes help, but again, GPUs are getting bigger. It's just a matter of time before they get big enough. And then finally, you've got the whole issue of botnets, which means that criminal elements have access to hundreds of thousands of computers that they can put to work on attacking password hashes if they get hold of them. And the cracking problem is, of course, massively paralleled. You can't think of a better solution for a better problem to attack with parallel computing. So this is the problem I'm trying to solve. Okay, and then the question is, at this point, there was a couple of earlier presentations on the keynote speaker from FTC and another presentation earlier in this room from NIST talking about increasing how to train people, how to get people to be more diligent in picking good passwords. What is a good password? There's a whole lot of churning about this. There's a recent story that Mark Zuckerberg of Facebook fame, his Twitter password turned out was hacked, and it turned out the password was ba ba ba. And if somebody at that level, who's a very bright guy, can be that sloppy in password picking, maybe we're trying to climb a hill that's a little bit too steep. You also have the problem that people reuse passwords, so damage from one attack can weaken other systems. And at some point, the industry, the problem is industry is trying to store this data. It really shouldn't be the responsibility of users to fix this problem. At some point, there has to be some way to solve this that is not dependent on users being ever more diligent in memorizing ever more longer passwords and even using diceware. Okay, and enterprise databases present an extra set of security challenges because they're in heavy use, and that means there are multiple applications from multiple computers, some of them accessing remotely. You can encrypting databases. I mean, there's this whole technology being developed called homographic encryption. Yeah, right, got that right. Anyway, where you can actually manipulate the data while it's still encrypted, but that's very cutting edge research, and it's not clear it will ever be really practical enough for day-to-day use. But in general, the problem with encrypting a database is that the encryption key has to be in the computer to access the database, and at some point this becomes sort of meaningless. Also, password databases have to be backed up. They have to be synchronized. All this adds more attack surface and more potential vulnerability. And the volume of password information is fairly small. I did a quick back of envelope calculation for 200 million users. The username plus hash plus salt, less than 10 gigabytes. And these days, 10 gigabytes, isn't really, is too inadequate for my watch. I mean, it fits in your pocket, and if you take the thing apart, you can probably, swallow it, and it's just a very small amount of data physically. And then finally, the attacker doesn't need the entire file. The attacker gets can get a few hundred kilobytes of the password, or even a few K of the password. They have something to attack. Okay. There are a bunch of alternatives: two-factor and biometric. They're cumbersome. Adoption has been slow. The typical user has lots of accounts, so that right now, you can get a dongle for your bank or a dongle for your company thing, but how many dongles are you going to carry around? And as far as I know, there are no good standards yet for interoperable dongles, and that will no doubt present another whole level of attack. There was an earlier report, and I guess it was discussed also in this morning's discussion. NIST is, I love having, normally I try to avoid having too many acronyms, but it's fun to put a bunch of them in one bullet point. But NIST is depreciating using SMS, text messages for out-of-band two-factor authentication because, as it was pointed out this morning, there are too many people. Like every clerk and every cell phone kiosk has the ability to generate an SMS card with a phony telephone number, so that the validation message that came through your phone could actually be diverted to somebody else's phone. So there's so many insecurities with that is, which was actually one of the things that's actually starting to work. People are getting used to using their phones as a authenticator. It looks like that's like too dangerous. And I'd also point out that without secure password storage, then two-factor. If you have a leg that's on, or something that's standing on two legs, and you cut down one leg, you only have one leg. Without secure password storage, two-factor becomes one factor. Okay. So that brings us to what is rock salt, and it's somewhat similar to salted hashing or keyed hashing, but it uses something that is sort of my invention, which I call very large key cryptography. And I use very large key cryptography to transform the salt. And in doing so, I make something that's hard to steal and makes physical security feasible. So let's talk about what this VLK concept means. And the idea here is to have a key that is actually much larger than the expected volume of data that's going to be encrypted. Now, at first, that seems like crazy, right? I mean, I have this little equation that cipher keys are much smaller than one-time pads, which in turn are much smaller than very large keys. It seems paradoxical. One-time pad is enough. Once you have enough key bytes to encrypt every single character separately, what's the point of going beyond that? And the answer is there are in fact some advantages to it. One of which is you can get provable security, and I can get That I think is going to be beyond the point of beyond the scope of this talk, but it's pretty easy to see why. But the most important thing for this talk is that you get a macroscopic key, a macroscopic secret, a secret that is actually physically big, okay? And that means it can be physically defended. And short leaks of that key, if you use it properly, are inconsequential, okay? The very large key, it would be random or possibly pseudo-random. That's a whole other discussion. It can be many terabytes, multiple solid-state disk modules. And you compare this with ordinary keys, which can literally fit on T-shirts and have in the past. That's a complete program for decrypting DVDs. And of course, the whole side channel problem where you're talking about a few dozen bytes. It's very easy to, not easy, but it's very feasible to monitor power usage or monitor radio frequency emanations, or a whole bunch of different ways of getting keys that are being used over and over and over again. The one example that I'm aware of that's somewhat parallel to very large key cryptography is deniable cryptographic file systems, where you basically fill a disk with random stuff, and then when you write data into that disk, you do it in an encrypted way, and hopefully if the encryption system is indistinguishable from pure random data, nobody looking at the disk can tell what's data and what's nonsense. So that, and the point there being that you could then reveal part of what's there without revealing all of it. But so far, that's the only precedent for what I'm talking about that I know about. Okay, so let's go into a little bit more of the details, and it's not complicated at all, really, once you get past this point. Normal password verification using SALT. You look up the SALT, and look up the using the username as a key. You look up their stored hash and SALT in a database. You hash the password that was submitted with that SALT. Does that match the stored hash? If yes, you're in. If not, you're not in. Okay, everybody's familiar with this, I hope, at this point. Okay, rock salt is not that different. Again, you look up the stored hash and SALT in the database. And let me just go back a second here. Obviously, there's another step here which I'm not illustrating here, but it's straightforward, which is when you first set up the account, of course, you take the password, you hash it, and you generate a random SALT, you hash the password with that random SALT, and that's what gets stored away in the database. Okay. For rock salt, the main difference is you still look up the stored hash and SALT. You send the SALT to the rock salt server. The rock salt server uses the SALT as a seed for a deterministic random number generator, preferably cryptographically strong, that picks out some number of bytes, enough for, say, 64 bits or whatever. There's an engineering trade-offs there, but basically nothing much different from ordinary SALT. You assemble those bytes and return it to the password server as the rock salt. And the rock salt, then the server does a hash of that trial password with the rock salt. If it matches the stored hash, great, you allow access. If not, you don't. It's not that different. Here's a kind of a block diagram of how that works. Users, again, they're accessing the computer. PMM is the password management module, which is typically a dedicated server or servers in a enterprise environment. That in turn communicates to this black box that I have down the bottom, the rock salt server. It can either be via whatever the corporate network is, or even better with an optional direct link. The password management module also talks to directly that little database symbol down there with the little file folders. That's just the ordinary corporate database. I'm not doing anything different to protect the corporate database. Obviously, you want to protect it if you can, but as I pointed out earlier, that's hard to protect. The only thing that's being protected here is this very large key that is literally stored in a safe. And on the left there, you can see my little sketches of how that would work. The solid-state memories would be put into little modules that might actually be keyed to make it hard to, some interlocks would make it hard to, not impossible, but just hard, slow down anybody who got physical access from trying to copy what's in that, and then the whole thing being locked in the safe. And again, once you have something that is physically large enough to protect, there's a huge amount of technology out there that's well established. You can obviously use a Faraday cage to minimize any stray radiation. You can attach alarm systems to this. One of the things about this is that the rock salt secret is static. So that means it doesn't require any periodic maintenance. The only reason to get in there is maybe an electronic failure that you have to replace one of the modules. So you can lock things in a safe. You can use, I don't know if everybody's familiar with it, but the whole concept of two-person integrity, where you have two different, it goes back to the, nuclear weapons launches, where you have to have two people turning a key to launch a missile, and certain government secrets actually require two people with a combination. That kind of technology can be used to ensure that no one insider can get at things. And again, with video surveillance, by making this thing big enough, the time required to copy the key or get meaningful amounts of data off the system is long enough that hopefully somebody would physically interrupt the process. You would presumably make more than one copy of this, so for an enterprise you might have several of them operating at the same time, and a few more of these modules kept in a vault somewhere as backups. There's tons of standards for both in terms of the electronic emissions from it and for the actual testing of safes. The NRA's laboratory has various standards. The General Services Administration has their Class 5 and Class 6 standards. There's all kinds of stuff out there that basically, these kinds of really fancy safes cost a couple $1,000s. If you think in terms of, again, an enterprise service situation, spending a lot of money to build a box like this that is secure, we're talking maybe, if we're selling this, tens, twenties of thousands of dollars, it's typical of internet appliances, and it's small compared to the what's at risk by having password data stolen. Another thing that can be used to protect us, since we do, obviously you have to have some electronic communication with this very large key, is to use a data guard. My data guard basically is a microprocessor or even an ASIC or FPGA that's just designed to pass only certain messages and at a rate-limited level, because the amount of data traffic required for the day-to-day ongoing minute-by-minute password verification is much less than the data rate needed to exfiltrate enough of that very large key to cause damage. These data guards can be made, they don't need an operating system. They can be very simple, easily audited software. There's a lot of, I think you can now actually get stuff that will take Haskell code and translate it into microprocessors. So you can have stuff that can be subject to proof systems. And you can actually have a series of different guards along the way. Some of which just limit the data, others of which we'll talk about in a second, make certain statistical tests to see if the things come under other kinds of attack. The alternative, the major alternative that I'm aware of is creating a separate database for password verification. Somebody asked me a question on the Peerless system. The name is 1337 Mark. Are we talking about a secure enclave for the passwords? And the problem with that is it complicates backup and synchronization of databases. Large enterprises may need to have more than one server and more than one password database to allow multi-continent operation of their business. All that synchronization creates more places where data can be stolen. And again, a small leak can cause compromises. Okay. So again, the big advantage of this is from the user's perspective is that we're back to passwords that are short enough that really people are comfortable with them. You still obviously have to limit or throttle failed login attempts so that a remote system doesn't sit there cranking away, trying to log in over and over again. But that's well established technology. People do that, and it doesn't require any new any changes to existing practice. The only thing you really have to avoid is obvious passwords, something that you can get from the Facebook account or some social engineering, pet names and stuff like that. Even the old, I don't know how many people remember the old AOL discs that used to be handed out, but they'd come in a little card and there'd be like a little your password on it that was 2 words with a special character in between. That would be more than adequate for this kind of thing. Even ba 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 would be fine. Okay. So potential attacks, obviously one physical security violation, again, the use of alarm systems and monitoring systems. Again, since this doesn't require anybody to access the system on a normal basis, one can be fairly strict in terms of using secure practices that are standard in industry. I think one of the major concerns would be malware that somebody sitting inside the corporate system and using the rock salt server to periodically, check passwords and accumulate them and exfiltrate those out. I think the answer to that one, there's a bunch of different answers there, one of which is to really have a secure link between the password server and the rock salt server, keeping track of how many requests and so on, maybe even add some canary passwords that would not normally be accessed. The basic thing to think about is that really if the software that's actually doing the password checking can be compromised, all the attacker has to do is get the passwords as they're entered. So you have to assume that for any kind of system that we have at least some integrity in the actual password verification software itself. Again, easy to guess passwords. I had put down using dictionaries to prevent users from selecting passwords that are too obvious. Actually, there was an interesting comment made earlier that actually may be counterproductive, because when somebody types in Rumpelstiltskin as their password and it gets rejected, they'll just type in Rumpelstiltskin 1, and that actually creates a set of passwords that are good ones to start trying. But again, there may be some training required here, or actually it may be desirable not to look at a dictionary necessarily, but look at things that you already know about the user, so that, for example, they don't use their username or the company's name or their personal name as their password. But this is, again, is a much easier challenge in terms of training people to just get them to not use things that are really closely, that somebody could easily guess about them. And of course, any password system is vulnerable to that kind of attack. So summing up, the advantages of rock salt: it's dependable, it's engineered, it can be proven its security can be proven from first principles. It eliminates the arms race because attackers don't get the opportunity to do offline password guessing, even if they get hold of the database. It's even quantum computing resistant, less burden on users. The changes to existing password management practices are very small. One has to set up this communication link and probably have some field in the database that tells you rock salt is enabled, but that's about it. And again, the password data itself, the verification data, just becomes part of the ordinary corporate database. It can be backed up, it can be handled no differently from any other user account information. The transition is easy. We've thought about how to fall. If people try this and they don't like it, coming up with a way to fall back to older systems if necessary. I think there's a confidence building step required here. But the bottom line is a lot less risk and liability for the enterprise, and of course, a lot less burden on users. Limitations, it's too cumbersome, I think, for small or personal operations. Again, using key derivation functions is probably the best bet for that. It's not a solution, as I said earlier, for passwords that are used to derive a cryptographic key. You can't use password hashes as a credential to share with other organizations or other parts of the organization, and that's not a good idea anyway. Business problems, obviously this is a new idea. Getting people to try it will be interesting. There are a lot of questions there, but that's maybe for another discussion. Finally, I want to say that this is not necessarily the most elegant solution. The idea of building this, terabytes and terabytes of information just to protect passwords seems clumsy, but I believe it works and nothing else does. And those of you who remember Raiders of the Lost Ark might remember this particular scene. Okay. Any questions?
I don't think there are any questions, so we can just Matt.
Okay, so this sounds like it has a lot of similarities to blind hashing by TapLink, which is they coined the term security through obesity by essentially having a very large hash database or a database that they would use in the hashing process.
And maybe I haven't seen it. I should look for it.
Okay, cool, thanks.
This is probably just my own brain fart because you definitely went into detail, but why is it that, how is the RSS server able to verify all these passwords if the trusted module is stored separately and securely?
Right, all the RSS server does, this is a good question. Let me see if I can get back to the little picture. All the RSS server does is effectively create a way of transforming the hash that was stored in the database to a different, the salt that was stored in the database, transferring the salt that was stored in the database to a different salt. And it does it in a way that an outside attacker has no way of knowing what that salt value is. So even though they get the salt that was in the database, they can't use that to calculate the hash that's stored in the database.
So is it a salt token? How is that different from a salting token that represents the actual salt?
I mean, I'm not sure it is. I'm not sure. The difference here only is that by using a very large key, you can defend this process. That's the novelty. A keyed hash will do this, right? But a keyed hash, you have a 128-bit or 256-bit key in that hash. You have maybe you're using a hardware security module. Maybe somebody develops a new side channel attack to that module. It's a single point. It's a very, very fragile single point of failure. The novelty here is using this very large key.
Can you go back one frame or slide? So, is that accurate?
I think so. Maybe if
okay, so there's a salt in the database.
Right.
Then you take that salt, give it to the rock salt server.
Right.
It returns a salt for you.
It returns a different value.
Yeah. And then you hash that.
Yeah.
So what's stopping someone from getting into the server, grabbing all the salts, requesting the rock salt server for all of those?
Right, and I mentioned that earlier, and that is. Let me see if we can get down to that. The main thing is to use a data guard that limits the rate at which you do this, and then also maybe has statistical tests that say, there seems to be a large number of. I believe you can get statistical patterns for what normal access is, and to distinguish between a systematic search. But yes, that. And then the other point is that in this whole system, I'm assuming that the server that is actually doing the password, when you attempt to log in, a password field gets sent to some server somewhere. That server then tells the rest of the system, yep, it's okay, or no, it's not okay, right? if that server can be compromised, you don't have to do anything more fancy than save all the passwords that get typed in. So we have to assume that there's the ability to make that server reliable. That has to be trustworthy, because if it isn't trustworthy, like I say, you just grab the passwords directly. Why bother with anything else? So if you can make that, reliable, that becomes the only thing that has the ability to talk to the Roxol server. It has a secure link, so the Roxol server is looking for its signed messages from it. Whatever, there's a variety of ways you can secure that link, but the idea is to make that link secure so that it's not easy for somebody to infiltrate software and do exactly what you're saying. But that of course is the trick that has to be prevented.
So it sounds like your big win here is that you're protecting from the particular attack, like offline attacks. So
Right.
somebody can't just get to the database and then do as many offline attacks with as many like GPUs as they possibly can.
Right.
And you still have a bunch of the same problems that existing systems do, but you've really locked down the offline
Right.
attacks.
But if you were here earlier, I mean, it's the offline attack that's driving everybody crazy. I don't know if you heard the keynote, but the young woman who was speaking was talking about, the fact that, large numbers of people are not with the requirements for people to change passwords. They're using closely related passwords. So once you get their password or one or two examples of that password, you can figure out their whole practice and maybe try it out on other systems. The whole thing becomes an arms race, and the arms race is not in the favor of people trying to defend.
So it sounds like the difference here between what you're doing, I mean, there are obviously some mathematical differences between what you're doing and the idea of doing a keyed HMAC on the hash. But aside from that, it sounds like the fundamental difference here is that the secret that you're using is fundamentally larger than the secret that might necessarily be used in say an HSM for doing an HMAC. Is that correct?
That's correct. That's exactly
Okay,
exactly correct.
So basically, your assertion here is that it's easier to protect a big key than it is to protect a smaller key.
Yes.
And I guess I don't accept that that's necessarily the case. I mean, a lot of the things that you're talking about doing here in terms of protecting the rock salt server are things that you could do just as easily on an HSM to protect the HMAC process.
Right, but how, again, how would you, for example, take for example the question of side channel attacks. With an HSM, you could get, if somebody came into the facility, set up a monitoring thing, which, the cleaning person or whatever, got we're talking about 32 bytes of data here. There's no way you could have any confidence that never happened. Whereas with this, you have it's an engineering thing. You have some engineering ability to say, I know what the amount of data is. I know solid state drives actually can't be read out very quickly. You can actually so you have a whole bunch of again, so it's a defense in depth engineering solution that says, I at least have the ability to get some confidence. I can review my monitoring tapes. I can do a whole bunch of things to say that data has not been stolen with some confidence. Whereas with an HSM, maybe.
Well, we'll just leave it and say that I think there are ways to protect against those side channel attacks in HSMs as well. The other part of this, though, is, unless I missed it, you didn't say anything about the size of the salt that you were using here, because
Well, I
in
think
the other case we had I think perhaps a 32-bit salt, which is enough in order to essentially solve the deduplication problem. Here you're asking for an additional level of security from it that would require a much longer salt, I presume.
Well, I didn't talk about it, and I can. The short answer is there are a couple of things you want to do, one of which is there are a couple of engineering trade-offs. It's a salt at 64-bit or 128 bits is not a great expense in terms of databases and stuff like that. and then the rock salt, sorry, not even a question of database, in terms of transmitting data back and forth. And there's actually a bunch of trade-offs I've considered here. But one of the reasons you want it a little bit bigger is there's always, I mentioned that small amounts of data leaked from the very large key don't do damage. The reason they don't do damage is that probability would be you might get 1 or 2 or 3 bytes. So you want to have the salt large enough so that 1 or 2 or 3 bytes being compromised doesn't reduce its efficiency. But it's not a huge increase in size. And there's some actually other options here too, one of which is actually set a different mode, which I talk about in my paper, is sending the password to the rock salt server and the hash, and the salt, and letting the rock salt server do all the calculation, then just only send back a single bit which says yes or no. So that would even further reduce the amount of data that could leak out of the server. But these are engineering trade-offs, but they're not in my opinion, they're not that difficult or dramatic.
So you mentioned a deterministic random number generator on the previous slide.
Right.
Is there any security concerns about that random number generator that you would have to think about specifically with this problem where you have a very large key and you're trying to prevent exfiltration of even of a smaller key?
Really any decent deterministic random number generator will do. Think about what's going on. You're sending the salt, which becomes the key, the seed for that deterministic random number generator. That is going to pick out 32 or 64 bytes out of this entire 100 terabyte, 10 terabyte, whatever memory, and then that string of bytes will be the rock salt. So the secrecy is simply the fact that the attacker has no idea what's in that very large key. And in fact, you can then begin to do basic statistics given the volume of users and what is the probability of any 1 byte being used even twice. And you can make that relatively small so that in reality, the vast majority of bytes that make up that key will never have been seen before. So that's really where the security comes from.
Okay, I think we'll stop it there. Arnold will be around afterwards as well, outside in the hallway. So now we'll do our short break until 3 o'clock. And next speaker up is Jeff Goldberg from Agile Bits, makers of 1Password. See you back then. Thank you.